In problem number 1, we're going to see that this is our initial population, p sub 0, and our growth rate here is r, and since we want this in decimal, we're going to convert that to 0.05. And so we'll just put together the function that describes this. So a is a function of t. Remember, we're looking for being able to calculate population t years into the future. It is going to be equal to our model, p sub 0, e to the rt, okay, and filling in some numbers here, we get 100,000 times e to the 0.05t. Predict the population 6 years from now, so that's basically asking us to plug in 6 for t, and so we're going to have 100,000 times e to the 0.05 times 6, and we put that into the calculator and we get 134,986. A more familiar way to write x to the 1/2 is simply square root of x. We have a rule that says a fractional exponent gives us a root. So 1 divided by 2 gives us the second root of x, which is the same thing as square root of x. This is a transformation here of a parent function. The parent function is log. If I isolate this piece right here with the f in the parentheses, I can think about this as being the total y value that's being transformed. And so here and here is on the outside of the function. And then this part inside the parentheses right here is what I'm replacing here. So that's kind of an easy way to think about that. So on the outside I'm going to have 4. And then my function is log of the stuff I'm replacing x with, in this case, 7, x plus 9, minus 11 again on the outside. Okay, to solve this equation, we're going to subtract 197 from both sides. That gives us negative 160 equals negative 8 natural log of x. And then I'm going to divide both sides by negative 8. Gives me 20 equals natural log of x. And then I'm going to apply the inverse of the natural log, which is e raised to a power. And the power is going to be each side here. Okay, so now I see that I have e raised to the power of log base e, natural log. Those are inverse functions which will undo each other. And so I'm going to end up with just my x, and on this side e to the 20th. This is a perfectly good number. If your answer choices list out some digits, some numbers, then you'll want to plug this in the calculator and match up whichever one it is. But this is a good answer. Here we can recognize that 25 is the same as 5 squared, and so we can use common base here to simplify things a little bit. So let's just go ahead and write 25 as 5 squared. Okay, that's this part right here. We still have the 2x plus 1 exponent. And now we're going to apply the exponent property to multiply this 2 by this 2x plus 1. So I can distribute this in, and I'm going to get 5 to the x power is 5 to the 4x plus 2. Okay, go up here, and now since I have the same base, I'm just going to match up the exponents. 4x plus 2. Let's subtract x on both sides. That's 0 equals 3x plus 2. Subtract 2 on both sides. That gives us negative 2 equals 3x. And we'll divide by 3. X is negative 2/3. This next question is basically just asking what are the different pieces here of this model right here. Our initial population is always this quantity right here, because if we plug in t equals 0, and that's what we mean by initial, t equals 0. If we plug in t equals 0, our exponent is 0. E to the 0, anything to the 0 power is always 1. 3750 times 1 is 3750. That's our initial population. The growth rate is our r value. That's right here. We have a decimal. We want to express that in terms of percent. So 0.2 is 20%. What is the population when t is 5? Well, we're basically just going to plug in 5 for t. And so we'll have 3750 e to the 0.2 times 5. If we put that in the calculator, we will get 10,194. In number 7, we're going to be solving for t. I don't have a number here, but I'm just going to leave this as a. And of course, e is our natural base, and we're not going to plug in a number for that. We'll just leave it as the number e. And so from here, we'll just go ahead and solve it like we've been doing a lot of the examples. I want to isolate the exponential first, so I'm going to divide both sides by 10. And now I'm going to apply the inverse of e to the power in order to get this exponent out. And that inverse, of course, is the natural logarithm, log to the base e, which we write ln. So we do that on the left, we do that on the right. And then we recognize that this log and this exponential undo each other as inverses, and so log of a over 10 is simply 5t. And then to isolate t, we're just going to divide both sides by 5, and we will have t equals log of a over 10, everything divided by 5. Rewriting an exponential as a logarithm is basically just remembering that if I have y equals b to the x, that's the exact same thing as log to the base b of y equals x. And so I'll just rearrange the furniture here, and I'm going to say log to the base 7. 7 is going to be b here, of y is equal to x. Expand this logarithm. And so when we expand a log of a quotient, we're going to be subtracting the log of the numerator minus the log of the denominator. So we'll start off with that. Log base 7 of 49 minus log base 7 of x squared minus 9. Okay, at this point you've basically done the job by expanding, but if you look closely, you can see that there's some more opportunity perhaps to expand this further. So 49 is the same thing as 7 squared. Here I have a base 7 logarithm with a base 7 exponential inside, so that's going to work out a certain way. Over here, this x squared minus 9 can be factored as the difference of two squares. Okay, and so now I have a log of a product which I can expand also. Let's go over here. When I have log to the base of a number to a power, that power can come outside by the power property. Okay, and I'm going to put this in parentheses just to keep everything straight. Over here I have log of a product, which is going to be the sum of the logs of each piece of the product. Okay, and then finally I'm going to look at this thing and say, well, this is log to the base b of b, so anytime I have that, this is equal to 1, and so my final answer could be something like 2 minus log base 7 of x minus 3 plus log base 7 x plus 3. I could go further and distribute this negative sign in here and so on. So maybe a couple more things I could do to rearrange this. Again, if you stopped here, that's fine, but I just thought this was an interesting problem in the sense that there was more breaking down that we can do here. How do we condense two logarithms? We recognize that we have log minus log, which is going to be log of a quotient ultimately, but also we have numbers outside the log which we can put back inside as exponents. So my first step would be to write this as an exponent, write this as an exponent on the inside. Okay, now I can combine these into one expression with the x to the 1/2 on top, y to the 5th on the bottom, and then one last simplification, if you will, x to the 1/2 as we saw earlier, square root of x, y to the 5th down below. Okay, we have a parent function e to the x. We're going to vertically compress by a factor of 1/3, reflect across the y-axis, and shift down by 2 units. And so to do that transformation, remember that the vertical compression is outside of the function. That affects the y value as well as shifting down. And then reflecting across the y-axis just means that we're going to change the sign of x. And so on the inside we change the sign of x. On the outside of the whole y value, we're going to compress by a factor of 1/3 and shift down by 2. Next problem, pretty similar. Now we're reflecting across the x-axis, which is changing y values to their opposite. Okay, vertically stretching, that's also a y operation. Shifting left 4 units is x, and so we'll go ahead and we'll write natural log, and we're going to shift left by 4 units. So on the inside, we'll change x to x plus 4, and then on the outside, we'll take care of our two transformations here. We have a change in sign, and we have a vertical stretch by a factor of 9, so we can combine those two into that. Number 13, if you were to look at your parent function for e to the x, you would be able to see, okay, if I change the sign of x, I now have exponential growth instead of exponential decay instead of growth. So here's the parent function right here. If I reflect that, my graph looks like this, and this is going to approach the x-axis, y equals 0. However, I am also shifting this graph up by 3, which means that now my exponential will be 3 units above, and so ultimately as x goes to positive infinity, y is going to approach that shifted value of 3. On problem 14, go ahead and graph this function on your calculator so that you know what it looks like in some detail. So that's not a great sketch, but if you have this on your graphed on your calculator or on a computer screen, then you can see the similarity, hopefully. What is our domain? The domain is all the x values that give us y values, and if we plug in x equals 0, well, this is an asymptote, a vertical asymptote here, so we get no y values there, and apparently no y values for negative values of x either. So a few different ways to write this. We can say all the values from 0 to infinity, but not including 0, so we have a round bracket. We could say x greater than 0, or we could say 0 is less than x is less than infinity. So a few different ways to write that. The range, this is going to go all the way to negative infinity. And even though this looks like it's leveling off, it continues to grow as x goes to infinity. This will get higher and higher and higher. It just goes very slowly. So our range is actually all real numbers. Again, we could write this as negative infinity is less than y is less than positive infinity. We could write an interval of negative infinity to positive infinity and so on. Where is this function increasing? All the way from its start to its finish. So everywhere on the domain. So that's going to look like the same as interval as the domain. Where is it decreasing? It's never decreasing. Where is it concave up? It's never concave up. Remember, concave up means curved upward. So could be like that, could be like this. Concave down, looks like it's concave down everywhere. It's curved down. Even though it's increasing, it's still curved down. So we can, again, use the domain as the interval for concavity because it's concave down in the whole domain. Where's the y-intercept? Well, this graph never touches the y-axis, so there is no y-intercept. The x-intercept is right here, and for all log functions, for all bases of log functions, that is always at x equals 1. Okay, so log to the base b of 1 is always 0. And again, if we rewrite this as an exponential, we can see that b to the 0 equals 1, which we know is true for any value of b. As x goes to infinity, f of x goes to what? Well, as x goes farther out here, my y values will increase slowly, but they will increase, and so they'll eventually get to plus infinity. As x goes to negative infinity, well, there's no y values out here, and so we really can't say anything. That doesn't exist. How about as x goes to 0 from the positive side? Remember, that's what this plus means. So my x values are going this way, approaching the x-axis, or the y-axis rather, and so I can see that my graph, the y values are going to head towards negative infinity, again because of the vertical asymptote. F of x is asymptotic to the x-axis. That means that the x-axis is an asymptote of f, and that is false. Okay, the x-axis here is not an asymptote. However, the y-axis is an asymptote. It's a vertical asymptote, and so that would be true.